Here we go again. Okay, today's lesson is on analyzing polar graphs. This is learning target number 6, analyzing the graph of a polar curve including domain, range, continuity, symmetry, boundedness, max R values, and asymptotes. Notice that list came mostly from our properties that we learned earlier this year in Unit 8. Okay, so you spent some time yesterday going through the properties of polar graphs, the max R values and symmetry. And you saw different equations that looked different shapes. And that's because we have several categories of polar graphs that we're going to analyze. One of those main categories is Rose curves, which are graphs of polar equations in the general form R equals A cosine of n theta and R equals A sine of n theta. N and A, so here are our two equations. N and A are our two variables. N has to be an integer greater than 1 or greater, and A should be non-zero, otherwise you have no real function. So Rose curves have these characteristics. Your domain is negative infinity to infinity. If you kind of look at this equation, this is a little weird. Polar equations are a little weird. Your theta is what gets plugged in, and your R is what you get out. So you think about our normal equations are in the form y equals. These are now in the form R equals. Okay, so our theta is what we're plugging in. That's our x value. So this domain comes from theta. In Rose curves, I'm allowed to plug in any angle that I want. What I will get out, however, is only negative absolute value of A to positive absolute value of A, because the max value of cosine is 1. So that's the reason. All I'm going to get out is whatever that multiplier is out front. Okay? That range then, since our domain is what we plug in for theta, that range is the radius values. Okay. Any graph we look at of a Rose curve is going to be continuous. If you recall from Unit 8, that you can draw it all in one swoop of the pencil. So I'm just going to draw a sample curve here. Don't kill me for my poor artistry. Okay, this example is 3 sine of 3 theta. My example curve. It is continuous. You could notice that I could draw that all in one pen swoop. As far as symmetry goes, and you analyzed this a little bit yesterday, but I'm not sure you picked up on the patterns. When we have a polar equation in this Rose curve form, that n, that multiplier on the theta, if it is even, is going to mean that this equation is symmetric about the x-axis, y-axis, and origin, all three. If n is odd, so that number in front of the theta is odd, like my example, then it defaults to whether you use cosine or sine. And if you use cosine, you're going to be symmetric about the x-axis, which kind of makes sense because cosine is always adjacent, which is always that horizontal piece, the x-axis. And if you got sine, then it's symmetric about the y-axis, which you see here in our picture, if you look at our example. All of the graphs are bounded, meaning they're not going to extend past that max R value, which happens to be the absolute value of A. Whatever your highest value in your range is going to be your max R value. There will be no asymptotes whatsoever. And the number of petals is also determined by n. So n does a few things. N determines symmetry, and it determines the number of petals in these Rose curves. If you have an odd number, like my example, the 3, then you will have n petals. So my 3 here in my example is causing me to have 3 petals on this graph. If you have an even n, then you double it to get the number of petals, which we'll see an example of here shortly. Okay, so our first example is 3 sine of 4 theta. First thing you want to do is graph it. When you do, you should see a curve that looks just like this does, with 8 total petals. So we're going to work our way through. First thing, domain. For any Rose curve, you can plug in any number you want, negative infinity to infinity. The range that you're going to get out is all about the A value. So we've got our A and our N. Range is going to be from that negative absolute value of A, negative 3, to the positive absolute value of 3, positive 3. Okay, and that's because we can plot any one of these extremes, which are on the 3's, okay, 3 away from that polar axis, by either rotating a positive r and then theta, or a negative r and a different theta. Okay, so our range is -3 to +3. Is it symmetric? Well, looking at it, it is definitely symmetric, and it's symmetric about all 3. The x-axis, y-axis, and origin. And we know that because we can see it in the graph, but we also know that because that n is even, and when it's even, it's going to cause that symmetry. Maximum R value is going to be that maximum that you have in your range, 3. And the number of petals is going to be double n, because n is even, 8, which you could also see from the graph. Example 2, 5 cosine of 3 theta. If you graph it, you should get a graph that looks like this, 3 total petals. Again, we can plug in any number we want for a domain. Range that we get out is going to be that negative absolute value of A to positive absolute value of A, -5 to 5, because we can plot these points by either going a positive radius with a theta or a negative radius with a different theta. Is it symmetric? This one does appear to be, but not in nearly as many ways as number 1. It does appear to be symmetric about the x-axis, which we know is true because your n is odd, but you are dealing with cosine. So when n is odd, it's symmetric about one of the axes, and since it's cosine, it's going to be the x-axis. Maximum R value comes from your maximum value in the range, 5, and you can see from the picture there are 3 petals, or you can use your equation. N was odd, so there should be that exact number of petals. What I want you to notice is that the blanks here in examples 1 and 2 didn't ask about continuity, boundedness, or asymptotes. Why would that possibly be? Why would we not need to ask about those 3 things for Rose curves? Well, it's because every single Rose curve is continuous. You could draw any one of them with one pencil stroke. Every single one of them is bounded on their domain, and absolutely none of them have an asymptote. So we're not going to ask that question every time, because it would be the same repetitive answer every time. But this is something you should know. All Rose curves are continuous, bounded on their domain, and have no asymptotes. Okay, moving on. The next type of curves we're going to focus on, this is the second of our 2 main types, are Les Maisons curves. And that's a little bit of a French word. You see that lovely little hanging do, I don't even know what it's called, on the C that gives it that S sound. So the Les Maisons curves are polar equations in the form A plus B, plus or minus B cosine of theta, or A plus or minus B sine of theta. So we have 2 different equations for Les Maisons. And this involves that addition and subtraction, which is what changes it a little bit. And notice that we no longer have a multiplier on our theta. We just have a straight up theta, 1 times theta. Okay, so these notes have a typo. A cannot equal 0, and B has to be greater than 0. A and B we're dealing with separate from that plus or minus, kind of like we did in the sum and difference identities. So A can't equal 0. So if it were 0, this would be a Rose curve, because it would be that A plus n times theta. So A can't be 0, B has to be something greater than 0, so that we're not multiplying by 0 and getting rid of sine altogether. We've got 4 different types, and it's all about the ratio of A to B. If A over B is less than 1, you're going to end up with a situation where you have what's called an inner loop, where you're going to have part of a curve inverted. Again, forgive me for my poor artistry. Part of a curve inverted inward into the other curve. Cardioid, if A over B equals 1, so if A and B are the same value, you're going to end up with what essentially looks like it's trying to be an inner loop, but it never actually made the loop. It's going to touch 0, 0, and it's going to be kind of like this little bean. Dimpled is the same idea. So if A over B is between 1 and 2, it's the same idea as cardioid, except that dimple does not necessarily occur on 0, 0. It occurs off of the 0, 0. Okay? And then finally, convex kind of just looks like you flattened it out. So it's going to be just a little kind of flat surface before it starts to round back out. So it kind of looks like an oval if you look at it on a graph. Lee Masson curves have the following characteristics. Again, our domain, our theta values, we can plug in anything we want. Our range is a minus b to a plus b. And again, you need to ignore the plus or minus that's in between. You use the number b and the number a, and that's it, as the whatever values they come in. Every Lee Masson curve is continuous. You notice as I drew those, with the exception of my poor drawing and having to go back and fill in, I could draw it with one pencil swoop. Symmetry in these are all dependent on whether it's sine or cosine. Sine goes with the y-axis, cosine goes with the x, just like they did when those petals, or when that n value is odd in rose curves. They're all bounded if you kind of look over these pictures. The max R value is going to be whatever the max was in your range, and there should be no asymptotes whatsoever. You're not extending anywhere because you're not bounded. Okay, so we've got a couple examples of these. The first is 3 minus 3 sine theta. If you graph this in your calculator in the window we've been using, you will not see the whole curve. So you will notice that in my graph over here, I have extended my y minimum to negative 1, 2, 3, 4, 5, 6, 7. So my y min is now negative 7 instead of negative 5. Okay, again, just like with the rose curves, we can plug in any theta we want, negative infinity to infinity. The range we'll get out is our a and our b subtracted and then added. 3 minus 3 is going to get you a 0 as your min, and 3 plus 3 is going to get you a 6 as your max. And if we look at this graph, you can see that the closest I am to the pole is on the pole, 0 away as our range for our r. And the furthest I am is down here at negative 6, which you could get to with a positive r value of 6 and rotating around. Okay, so my range is from 0 to 6. Is it symmetric? Why, yes it is. All of these Lee Masson curves will be. And how do we determine? Well, you can either use your picture or use your equation. When we have sine, it should be symmetric about the y-axis, which if you look at this one, it is. And the max R value is going to be whatever the maximum was in your range. 6 is the max. Example 2, you can go back to your normal window for 2 plus 3 cosine of theta. You should get a graph that looks like this kind of little Mr. Pac-Man. Our domain is negative infinity to infinity because we're always allowed to plug in whatever theta values we want. Our range here is going to look a little different because of this inner loop. I've kind of gone backwards. Okay, so I've inverted myself. If I use my a and my b and I do a minus b, I'm going to get negative 1 as my range. And you see this has inverted into my bubble 1. Negative 1 to the maximum a plus b, which is going to get me 5, which you can see over here on this extreme. So this got inverted the 1, there's where your negative comes from, and then we go over 5 for that positive maximum R value. Is it symmetric? Again, yes, all Lee Masson's curves will be. You either use the curve or you use the equation. Since it's cosine, you're going to be symmetric about the x-axis. Again, just a little side note, these blanks, again, didn't ask about continuity, boundedness, or asymptotes. Why in the world would that possibly be? Well, when we listed those properties, we said that all Lee Masson curves are continuous, are bounded on their domain, and have no asymptotes. So we're not going to ask those questions over and over again. However, we are going to be expected to know that all those curves have those 3 properties. One last little thing I just want to quickly introduce to you is the spiral of Archimedes. And it's not one that we're really going to focus on, but it's a fun one, and that's why I wanted to show it to you. The spiral of Archimedes is in the general form R equals A plus B theta. So you'll notice that this equation no longer has a sine or cosine value as part of it. It's just all about the R and the theta. And what that means is your window, if you try to graph this, is going to have to be pretty drastically different. You have to zoom out pretty far to be able to see any part of this spiral. But it's unbounded, it has no symmetry, and it has no max R value because it really kind of just looks like you're going into the twilight zone. It's just a spiral that continues to go on and on and on and on and on. And with the exception of that last little piece, I was doing pretty well. They should be spaced evenly as you go through and just continue to get bigger and bigger and bigger. So it's just a fun little design, which is why I wanted to introduce it. Those are our main three. So we're going to focus mostly on Rose and Lee Mason. And it's important that you know the properties of these two. But I would like you to also recognize the spiral of Archimedes when you see it or when you see an equation.